Hello everyone. So today we're going to continue learning about assembly language programming on the Atari 8-bit computers. We're slowly going through this Atari Roots book, and today we're going, and all these URLs are going to be in the description. We're going to go to chapter 3 today inside the 6502. And you can follow along on the web browser, but I'm going to be reading from the PDF because it looks a little bit more like a an old school book, and we want that nostalgic sort of feeling. I was thinking about it, and one of the things I realized compared to my other series on Nix that like this book is really basic. Like there's not me reading it with you, at least, the binary stuff, like it wasn't hard. So really just like you probably already know binary. But if you didn't, you learned it with Penguin Math. But it wasn't hard. Like you could read it and you would get it. So I feel like, I'm not adding a lot. And at least today we're going to learn about the 6502. Someone left a comment like, hey, you're going to just keep writing in BASIC and like doing peeks and pokes. That's going to kind of suck. And I was like, yeah, that's the feeling I got. This book is really good because it's so easy to follow for anyone, but at the same time, it's super slow. So, next chapter, chapter 4, is when we're promised that we're going to start actually programming assembly. So if that's why you're here, then just wait, subscribe and wait for the next video. Or maybe it's already out by the time you're looking at this. But at least for me, I'm excited about this chapter because now, like, I don't know anything about the 6502 really, other than it's like a very simple CPU. So this will be kind of interesting and fun for me. Yeah, like the idea of this series, in case you're new, I'm Elise, and I'm learning along with you guys, hopefully, or you just already know it and you just want the nostalgia of like talking about it. Um, yeah, as opposed to like some of these tutorials where the person's an expert, they go over and you're like lost halfway through and it was just a waste of your time. Well, I'm lost all the time, so if I learn it, then you definitely should be learning it too. And there's a Discord server if you ever get lost. It's in the links in the description, so that if you have any questions, you can come and ask. All right, so let's get started. We're going to finish chapter 3. I don't care how long this takes, but we're going to finish it so that next video we can actually start programming. We're going to be using the Mac 65 assembler. You see a little bit of my Atari emulator here. I don't have a real Atari, so I'm using the emulator. But yeah, like we'll be using the Mac 65. I don't think there's anything else, and we're using the Altera emulator. The first video talks about how to get those things and where to get it. So let's get into it. All right, that was the intro. Starting inside the 6502. In this chapter, we're going to get under the hood of your Atari computer and see how it works. Then you'll be able to find your way around inside your computer and at least start doing some assembly language programming. Yes, we want to get there. Hurry up. As we explained in chapter 1, every computer has 3 main parts: a CPU, memory, RAM and ROM, and input and output devices. They love repeating stuff, right? In a microcomputer, all the functions of a CPU are contained in a microprocessor unit, sometimes abbreviated MPU. I never heard of MPU before this. Have you guys? Say in the comments, because that's new to me and I've been doing computers for a bit. Your Atari's MPU is the 6502 microprocessor. All right, well, I just say 6502 CPU all the time. So, all right, we got a data bus and an address bus. We got memory. Data bus, I guess, is like when you transfer information, right, between the different components. And address bus, I guess, is to access memory. I don't know, like address, I assume, is like a memory location. And then these are probably like registers, program counter, I'm guessing. XY are probably accumulators. Arithmetic logic unit, maybe. A, probably an accumulator. Input output, I think that's a keyboard and screen. So let's see how much. I have no idea what this P is. If you guess, let's see if you're right. The 6502 microprocessor contains 7 main parts: an ALU, that's what we said, and 6 addressable registers. 1, 2, 3, 4, 5, 6. I guess that's it. Data is moved around inside your 6502 chip between the 6502 and other components in your computer over transmission lines called buses. All right, so those are the two buses, data bus and address bus. There are two kinds of buses in an Atari computer, an 8-bit data bus and a 16-bit address bus. The data bus is used for passing 8-bit data and instructions bytes from one 6502 register to another, and also for passing data instructions back and forth between the 6502 and your computer's memory. Oh, interesting. The address bus is used to keep track of your computer's 16-bit memory addresses, the addresses that instructions and data are coming from, and the addresses that instructions and data are being sent to. Wait a minute, so didn't it say here that it's for passing data to the memory? Which is, an address, right? And the address bus is used to keep track of your computer's 16-bit memory addresses. Like, how does a bus keep track of addresses? We'll find out. This is the first time where I feel like they failed. They failed explaining. But we'll get there. If it's like everything else, they're going to repeat it 20 times. The arithmetic logical unit. This should be a chapter. The most important component in your computer is the 6502 chip. And the most important part of the 6502 chip is its ALU. Every time your computer performs a calculation or logical operation, the ALU is where all of the work is done. The ALU can actually perform only two kinds of calculations: addition operations and subtraction operations. Division and multiplication problems can also be solved by the ALU, but only in the form of sequences of addition and subtraction operations. That's interesting. The ALU can also compare values. All right, so I guess that's not a calculation. It compares values by subtracting one value from the other and then noting the results of the subtraction operation. So it just subtracts and then it sees if it's greater than 0 or not, probably, or if it has like a overflow bit flipped. The 6502 chip's ALU has two inputs and one output. When two numbers are to be added, subtracted, or compared, one of the numbers is fed into the ALU through one of its inputs, and the other number is fed in through the other input. The ALU then carries out the requested calculation and puts the answer on a data bus so that it can be transported to wherever it's needed in the program. So when we looked at the ALU, here's the ALU. And we look at the input, there's one input coming in here, right? And this is sort of like maybe an input because it goes both ways. And this is the data bus. I'm assuming this is more for like putting stuff on, but it's not clear when they say there's two registers for the ALU where that's coming from. Right? Okay. In diagrams of the 6502 chip, the ALU is often represented as a V-shaped hopper. Do you guys know what a hopper is? I think I played a video game where there was a hopper. It was like crafting, so you put stuff in there and the hopper just has like an output after it's done with whatever work it's doing. So that's like where the crafting stuff comes out. So I'm guessing a hopper here is like you put stuff in, you push the button, and then like it outputs the answer. The arms of the V are the ALU's input, and the bottom of the V is the ALU's output. So this is the output, even though it's kind of pointing in both ways. This is the input, and that's the input. So this is saying that one input's from the register and the other input's from the data bus. Is fed through the other input. I guess we don't know what the other input is, right? When calculations or logical operations is to be carried out by the ALU, one piece of data and an operand, an addition or a subtraction instruction, are deposited into one of the ALU's input, one arm of the V. The other piece of data is deposited into the other input, the other arm of the V. When the calculation has been performed, its result is ejected, very powerful ejection, through the ALU's output, the bottom of the V. All right. Well, we have questions. We need answers. The accumulator. The ALU never works alone. It carries out all of its operations with the help of a 6502 register called the accumulator, abbreviated A. Is that what it has over here? Yeah, it says A. So this is the accumulator. When the ALU is called upon to add or subtract two numbers, one of the numbers is put on the data bus and sent to one of the ALU's inputs, along with an operand. All right, so we learned that it really does come from the data bus. I wonder how you put it on the data bus and say like, hey, you're on the bus, but go to the ALU. We'll find out. The other number is in the accumulator. When the bus carrying a number and an operand to the ALU discharges its cargo into the ALU, the accumulator puts the number it is holding on the data bus and sends that number to the ALU. Oh, so it puts it in the data bus and sends it to the ALU. Isn't that funny? Because it doesn't look like it's going to the data bus. It looks like it's going straight to the ALU, no? Well, when the ALU has carried out the requested calculation, it deposits the result of the calculation in the accumulator. So I guess it goes back to the accumulator. Suppose, for example, that you wanted your computer to add 2 and 2, and then place the result of its calculation in a certain memory location. You could use an assembly language routine like this one. LDA number sign 02. Was the number sign for decimal, right? So this means this is the number 2 in decimal, which makes sense. It could be hexadecimal, but this looks like hexadecimal because we see C and B. So I'm guessing number sign. Oh yeah, it's going to tell it. All right, so load accumulator, I'm guessing. Oh, it's going to tell us. ADC number 02, STA $CB. The first instruction in this routine, LDA, means load the accumulator with the value that follows. So in this case, that value is 2. The number sign in front of the 2 means that the 2 is to be interpreted as a literal number, not as the address of a memory location in your computer. Okay, so it's not a memory address that we then have to get a number from or something. It's just literally the number 2. Go put it in the accumulator directly. The second instruction in the routine, ADC, isn't that a league abbreviation? Means add with carry. All right, so now we finally know why League calls it ADC. That's a joke, guys. In this addition problem, there is no number to be carried. The carry part of the instruction has no effect here, and all the ADC instruction does is add 2 and 2. All right, so basically this instruction takes in the 2. It probably passes it in the data bus, right? And sends it to the ALU. And the ALU is going to have the number 2 already in the accumulator. It gets this number from the data bus. And then it's going to do it, and the accumulator will have the result. I think that's right. The third and last instruction in our routine, STA, means store the contents of the accumulator in the memory address that follows. As you can see, the memory address that follows the instruction STA is $CB, the hexadecimal equivalent of the decimal number 203. So we just have to remember $sign is hex. Maybe like a mnemonic is like hex is very rich. It's a very big number, so it's very rich. And dollars are rich. Okay. the hexadecimal equivalent of the decimal number 203. Since there is no hash sign in front of the hex number $CB, your assembler will not interpret CB as a literal number. Instead, CB will interpret it as a memory address, which is what a number has to be in assembly language if it is not a literal number. Incidentally, if you want your assembler to interpret CB as a literal number, you would have to write it hash $CB. When a hash symbol and $sign both appear before a number, it is interpreted as a literal hexadecimal number. All right, so you first write the hash before the dollar because maybe the dollar wants to stay close to the money. This is just how I try to remember things. If the third line of our sample routine read STA hash $CB, however, that would be a syntax error. That's because STA, store the contents of the accumulator in, is an instruction that has to be followed by a value that can be interpreted as a memory address, not by a literal number. All right. Yeah, you're not storing a number, you're storing it into an address, so it needs to be not a hash. 5 other registers. Besides the accumulator, the 6502 processor has 5 other registers. They are the X register, the Y register, the program counter, the stack pointer, and the processor status register. Here's a brief summation of the functions of each of these registers. All right, let's go into the other registers. The X register, abbreviated X, I think I would get it, is an 8-bit register that is often used for temporary storage of data during a program. But the X register has a special feature too. It can be incremented and decremented with a pair of 1-byte assembly language instructions, INX and DEX, increment X and decrement X, I'm guessing. And it is therefore often used as an index register or counter during loops and read data type instructions in programs. So like if you do a kind of a while loop or for loop 1 to 200, 1 to 50 or something like that, it sounds like the X register is a good one to use for that. Or yeah, I guess. The Y register, abbreviated Y, is also an 8-bit register and can be incremented and decremented with a pair of 1-byte instructions, INY and DEY. So the Y register, like the X register, is used both for data storage and as a counter. They said it's a special feature, but it's not a special feature, right? Like the X and Y are the same, so there's no special feature. Well, I guess it's special compared to most registers, but there's another register that does it. The program counter, abbreviated PC, is a pair of 8-bit registers that are used together as one 16-bit register. Oh, that's cool. The two 8-bit registers that are combined to make up the program counter are sometimes referred to as program counter low, PCL, and program counter high, PCH. This is when we learned about how we store 16-bit numbers in memory in the Atari, right? Like they're kind of swapped. The most significant bit is actually stored second. The program counter always contains the 16-bit memory address of the next instruction to be executed by the 6502 processor. When that instruction has been carried out, the address of the next instruction is loaded into the program counter. So it's just like basically pointing to where the code is all the time. And probably if we want to like jump to another memory location, just like go 250 in BASIC, like we're just changing where the program counter is pointing. The stack pointer, abbreviated S or SP, is an 8-bit register that always contains the address of the top element in a block of RAM called the hardware stack. The hardware stack, usually referred to simply as the stack, is a special segment of memory in which data is often stored temporarily during the execution of a program. We'll go into more detail about how the stack works later. All right, you maybe have heard of call stacks and stuff like that when you make function calls in C or most languages. It's probably similar to that. I don't know. The process status register, usually called simply the status register but abbreviated P. Why is it P? Oh, processor. Okay, processor status register is P. Is an 8-bit register that keeps track of the results of operations that have been performed by the 6502 processor. So, it's going to tell us more about it here. The processor status register. The process status register P is a little different from the other registers in the 6502 microprocessor. It isn't used for storing ordinary 8-bit numbers as the 6502's other registers are. Instead, this register's bits are flags that keep track of several kinds of important information. Oh, this is the one, what are we on? We're on 49, right? So this is the one where they had all those little bits here, right? Yeah, P, we have NV minus BDIZC. Interesting. All right. 4 of the status register's bits are called status flags. They are the carry flag, the overflow flag, V for overflow, the negative flag, and the 0 flag. Okay, C for carry, V for overflow, N for negative, and what was the last one? 0 flag. Okay. These 4 flags are used to keep track of the results of operations being carried out by the other registers inside the 6502 processor. 3 of the P register's other bits, called condition flags, are used to determine whether certain conditions exist in a program. These 3 bits are the interrupt disable flag I, the break flag B, and the decimal mode flag D. The 8th bit in the status register is not used. Oh, interesting. Why would they not use it? I thought this was all about making the use of like every little bit back then. All right. I is interrupt flag, B is break flag, D is decimal flag. That's not too bad. And we have a pirate ship because of flags. These kind of things take me forever to figure out, like, what's the analogy here? Flags, but maybe they're sinking. 6502. Layout of the processor status register. The status register can be visualized as a rectangular box containing 6 square compartments. For those of you who aren't visual people, this is hard. I'm not sure this is easy for me. Anyway, each compartment in the box is actually a bit, and each bit is used as a flag. If a bit is a 1 instead of a 0, then it is said to be a flag that is set. If a bit is a 0 instead of a 1, then it is said to be a flag that is cleared. All right, so all this means is, like, for all of those flags that we just talked about, right, it's either going to be 1 or 0, and 1 means it's set, like it's on, and 0 means it's off. The bits in the 6502 status register, like the bits in all 8-bit registers, are customarily numbered from 0 through 7. The rightmost bit is bit 0, and the leftmost bit is bit 7. So here are the bits in the process status register. It's 8 bits long, so overall, if you just take the register, it's going to give you a number from 0 to 255. We learned that in the previous thing. If you don't understand that, go back to the binary video and suffer. All right, 7 flags over Atari. I'm just trying to remember. Negative, overflow, break, decimal, interrupt, 0. C was clear. Was that right? Carry. I knew that was wrong. Damn it. Almost. Here's a complete list of the flags in the 6502's processor status register and an explanation of what each one means. Oh god, there's a lot here. I think maybe I'll try to make a cheat sheet that just like captures some of this information. Anyway, here we go. The bit 0, the rightmost flat bit, is the carry flag. As we saw in Chapter 2, it isn't easy to do 16-bit arithmetic with an 8-bit chip like the 6502. When the 6502 chip is required to perform an addition operation on a number greater than 255, or if the result of a calculation might be greater than 255, a program has to be written that will break each number down into 8-bit segments for processing and will patch all of the numbers back together again. This kind of mathematical cutting and pasting, as you can probably imagine, involves a lot of carrying if addition problems are being performed, and borrowing when the 6502 is performing subtraction. The carry flag of the 6502P register is the flag that keeps up with all of this carrying and borrowing. If an addition results in a carry, the carry flag is automatically set. And if a subtraction operation requires a borrow, the carry flag keeps track of that too. Since the carry flag is almost constantly being set and cleared as a result of carries and borrows in addition to subtraction, it's always a good idea to clear it before an addition operation is to be carried out and to set it before a subtraction operation takes place. Otherwise, there's a chance that your calculations will be messed up by the leftover results of previous addition and subtraction operations. So that's really interesting. Basically, if you do something that adds numbers, you have to clear the carry flag to 0, right? Like clearing it sets it to 0 because it might be set. But subtraction, like if it needs to borrow, it's going to take the 1 in the carry flag and turns it to a 0, it sounds like. So they actually say before you do a subtraction, you should set the carry flag, set it, then you know whether it had to borrow, right? So you're kind of doing opposite things whether you're adding or subtracting. And obviously, here's an example is like if you do 255 plus 1, it can't store 256, so it will set, when you try to add those two numbers together, it will set the carry flag. All right, and borrowing is if you subtract like a number bigger than the first number, right? Like 200 minus 255. In addition to keeping track of carrying and borrowing operations, the P register's carry flag is also used in operations involving comparisons of values, and in certain shift and rotate operations to check, compare, and manipulate specific bits in binary numbers. We'll discuss number comparisons and bit operations in later chapters. For now, it's more important to remember that assembly language instruction to clear the P register's carry bit is CLC, which stands for clear carry, and that the instruction to set the carry bit is SEC, which stands for set carry. All right, good to know. CLC, clear carry, and SEC is set carry. All right. Bit number 1, the second bit from the right, the 0 flag. When the result of an arithmetic or logical operation is 0, the status register's 0 flag is automatically set. Addition, subtraction, and logical operations. Sorry, I need a drink. Not like that kind of drink. I do not drink alcohol when doing technical stuff. Can I even say alcohol? I'm like, I try programming when I'm a little bit, after drinking, and it's just impossible. All right. Don't drink. Drink water. That's good. Addition, subtraction, and logical operations can all result in changes in the status of the zero flag. If a memory location or an index register is decremented to zero, that will also result in a set zero flag. The memory location or an index register is decremented to zero. Got it. An ironic 6502 convention is that when the result of an operation is 0, the 0 flag is set to 1, and that when the result of an operation is not 0, the 0 flag is cleared to 0. It's important to understand this concept since it would be easy to assume that the 0 flag operates in just the opposite manner. There are no assembly language instructions to clear or set the 0 flag. It's strictly a read bit or read bit. So instructions to write to it are not provided. All right. All that means is that flags are basically sent up or down, right? So when there's a 0, the flag is actually set, which means the 0 flag is 1. Which seems kind of counterintuitive, but it sounds perfectly intuitive to me. So I will continue. Bit 2, the third bit from the right, the interrupt disable flag. Yeah, I don't know what this is, so let's see. It's probably like IRQs or something, right? Some Atari programs contain interrupts, instructions that halt operations temporarily so that other operations can take place. Excuse me. Some interrupts are maskable interrupts because you can prevent them from taking place by including masking instructions in a program. Others are non-maskable because you can't stop them from taking place no matter what you do. When you want to disable a maskable interrupt, you can do it with a P register's interrupt disable flag. When this flag is set, maskable interrupts are not permitted. When it is clear, they are allowed. The assembly language instruction to clear the interrupt flag is CLI, clear interrupt. The instruction to set the interrupt flag is SEI. So, maskable to me usually means like bit masks, but here it's just a simple bit. You just say like, hey, I don't want interrupts, so you set it to 1, right? Let's see, where did it say that? When you want to disable a maskable interrupt, you can do it with the P register's interrupt disable. When the flag is set, maskable interrupts are not permitted. So when you turn on the flag, then you won't get those interrupts. I don't know what kind of interrupts you can get yet, but we will learn, and we will remember that we can set the P flag to do that. The P register, no, not the P flag. The P is the whole thing, and this is the I flag. Bit 3, the fourth bit from the right, the decimal mode flag, D. The 6502 processor normally operates in binary mode using standard binary numbers of the type that were discussed in Chapter 2. Oh, those were definitely discussed. But the 6502 can also operate in what is known as binary coded decimal, or BCD mode. That sounds kind of cool, BCD mode activated. To put the 6502 into BCD mode, you have to set the decimal flag of the 6502 status register. BCD arithmetic is slower than plain binary arithmetic, and it also consumes more memory. But its results, unlike those of plain binary arithmetic, are always 100% accurate. That sounds like a funny thing to say. Like, the computer is always going to be accurate. It's just you may lose. We'll talk more about it. Therefore, it is often used in programs and routines in which accuracy is more important than speed or memory efficiency. I see. Maybe what they mean by accuracy is precision. One example of a program that uses BCD arithmetic is your Atari Basic interpreter. In Atari Basic, all numbers are stored as 6-byte BCD numbers, and all arithmetic is performed as BCD arithmetic. Because of this feature, Atari Basic runs somewhat slowly, but its calculation yield accurate results. Another advantage of BCD numbers is that they're easier to convert into decimal numbers than plain binary numbers are. So BCD numbers are sometimes used in programs that call for the instant display of numbers on a video monitor as well. How many bytes did they say? 6 bytes. So that's a lot more, it takes a lot more bytes. We'll discuss BCD at greater length in Chapter 10, Assembly Language Math. For now, it's sufficient to say that when the status register's decimal mode is set, the 6502 chip will perform all of its arithmetic using BCD numbers. BCD arithmetic is rarely what you want when you use an Atari computer, so you'll usually want to make sure that the decimal flag is clear when your computer is doing arithmetic. The assembly language instruction that clears the decimal flag is CLD, clear decimal. The instruction that sets the flag is SED. Hey, at least they're consistent, right? Clear is CL, SE is set. All right, we're almost down to bit 7. I see bit 6 down here, so unless one of these is really long, we're almost there, hopefully. Bit 4, the 5th bit from the right. The break flag, B. The break flag is set by Special Assembly Language Instruction, BRK, break. Computer designers often use the break instruction in assembly language programs during the debugging phase. When the instruction is used and the break flag is set, certain error flagging operations take place and control of the computer returns to the programmer. The break instruction is a highly complex, sophisticated debugging tool, and we won't go into much detail about it in this volume, but you can learn more about it in some of the advanced 6502 programming texts listed in the bibliography. All right, this sounds very sophisticated. We won't need it because all of our programs will be correct the first time and we will not have to debug them, right? Bit 5, the 6th bit from the right, unused bit. For some reason, the microprogrammers who designed the 6502 status register left one bit unused. This is the one. Poor bit 5. Bit 6, the 2nd bit from the left, the overflow flag, V. The overflow flag is used to detect an overflow from bit 6. The next to rightmost bit in a binary number. If you don't know what that means yet, don't be concerned about it. The overflow flag is used primarily in advanced 6502 arithmetic, specifically to keep track of changes in the plus and minus signs of signed numbers when the signed binary arithmetic is being performed. As an Atari assembly language programmer, you'll rarely, if ever, have an occasion to use the overflow flag. Nevertheless, we'll discuss it at greater length in Chapter 10. Sorry, like if I go blank, it's not a seizure. I'm just thinking about something. Assembly language math. For now, all we'll add, just for the record, is that the assembly language instruction that clears the overflow flag is CLV. There is no instruction to set the flag. All right, so they said overflow from bit 6, which means that like when you add some numbers, the bit number 6 is almost the most significant bit, and if the most significant bit, then you can have like an overflow, I guess. But we'll learn more about it when we get to this Chapter 10. Bit 7, the leftmost bit, the negative flag. The negative flag is set when the result of an operation is negative and cleared when the result of an operation is 0. It is often used in operations involving signed numbers, and it also has other uses that will be discussed in later chapters. There are no instructions to set or clear the negative flag. There is no need for any since the flag is used for test purposes only. I think they mean testing, not as in like, hey, we made this, we weren't sure if we're going to use it. It means like, hey, you want to like check if it's set or not. So you're testing the flag. Your big chance. Now that you know what goes on inside your computer's 6502 processor, you're ready to write and run your first assembly language program. Guys, calm down. I'm not going to type in this fake basic program. They're not going to convince me that this is an assembly language program. But we'll look at it. You'll have a chance to do just that in the next chapter, but first, here's a chance to run another bonus program containing some machine language values that can be poked in from a basic computer. This routine, bonus program number 3, will turn your computer keyboard into a musical keyboard, type it and run it, and we'll take a look at how it works. Yeah, so there's stuff here. Sound off. This is just a remark, a comment in key. Well, let's just read here. In line 30 and 35, this program, the audio registers of your computer are cleared to 0, and a loop is set up to print characters on your screen. 30 and 35. This is the loop here. So graphics 0, this clears the screen. I think this opens input from your keyboard. And 32 is ASCII for space. So that's probably like making a sound or something. Print, this is the character that you're inputting, I'm guessing. Go to in key. This 32 is a space. Look at that. In lines 40 through 70, some checks are carried out to see if any of the characters that have been typed are valid notes A, B, C, D, E, F, or G. As some of you may know, especially Europeans, that's do, re, mi, fa, sol, la, ti. But actually, C is do, so this is do, re, mi, fa, sol, la, ti, or si, depending on your language. All right, so this is here where we're checking the letters. And you have both uppercase and lowercase, so here we go. Tone is equal to minus 65, minus 64, 65 is A, so it's basically mapping it back down to A, B, C, D, E, F, G. And now print the character and go to 1000. All right. If the character is low, it is automatically converted to uppercase in line 60. The subroutine at line 1000 is the audio registers in your computer are reset to play the notes A through G when corresponding letters are typed. Unless the character is a space, if the character is a space, all audio registers are turned off. That's what the 000 must have been, right? Like sound 0000 means like turn off all the audio registers or just reset them. Right. To wait for the next typed character that happens in line 35. The machine language instructions in the program are in the lines 100 through 700. 100 through 700. That's here. All of these pokes. Frequency 145. Go to in key. Interesting. What is in key? Where is in key? Is that like, oh, here? Is that it? Or 30? No. That's probably the line number here, right? In key equals 35, and it's saying go back to 35. I don't know basic, so this is a little bit hard for me. I'm here for the assembly. Why do they keep giving us basic? All right. If in those lines a certain memory register in your computer called frequency is stuffed with a value that equates to a musical note. Each time that value changes, the note being played changes accordingly. This is a very simple program that doesn't even begin to explore the complex sound capabilities of Atari computers. Still, the ways in which it can be expanded are limited only by the user's own imagination. Well, I don't have much. By making the program a little more complicated, you could add the capability of reproducing sharps and flats with the control key, for example. And you can also add more octaves, for instance, with the shift key, the number keys, or the shift control key combinations. You can make the screen change colors as the notes change, or you can save melodies in your computer's memory and save them on a disk, and you might even be able to figure out a way to play chords. You could do all of those things in BASIC if you wished, or if you are more ambitious, you could move beyond BASIC and continue to learn more about how to put your Atari through its paces using assembly language, which brings us to Chapter 4, Read On. All right, we're finally here. So we'll cover Chapter 4 next time. If you found this useful, please like and subscribe. There's all the other links that I talked about in the description. Join the Discord server if you want to talk about it or have any questions. And hopefully soon we'll be actually typing in assembly. So you're going to need to get this like Max 65 assembler. That's what I'll be using. I guess like you could be using the Atari assembler editor cartridge too, but I won't be showing how that actually works. And we're going to have fun doing that in this other like screen here that is the this full Atari screen here that we did nothing with today. It's very sad. Thank you everyone. Talk to you soon. Enjoy.